to introduce the next speaker will be George Kattawar. George got his PhD in physics from Texas A&M, moved around Texas for a bit, and then got back to Texas A&M in 1968, where he's been since, just recently retiring, sort of, but continuing to work a lot. He's a professor emeritus. He has over 175 published peer-reviewed papers. He won the Yerloff Award this year in October, and he told me just recently that he's won the Vanderholtz Award for light scattering and radiative transfer. In June, he has to travel to Europe to do that. George with Howard are recognized as many of the leaders in using radiative transfer in the ocean and atmosphere. And George was also on my committee a long time. So anyway, so welcome, George.
Thank you, Ken. Appreciate it. Well, first of all, I want to thank Ken for inviting me to this most auspicious occasion. And it's certainly a pleasure to be here with my old friend and colleague, Howard, who I've known for many years, admired his work. And the thing I really particularly admired was his rigor for physics, because we both had physics background. I knew some of the guys he worked with even when he was a student, talks to them. Yeah, they're great people. But anyway, just to show my appreciation for all the work that Howard's done over his many years of work in ocean optics, I'm sort of a hack amateur wood turner, and it's my hobby. So Howard, I want to present to you a pen I made for you. It's a nautical pen, which has an anchor pin clip on it, and ships, steering wheels, and ships here. It's a twist pen made with black and white ebony, and I want to present this to you. You're welcome. My pleasure. Let me ask, is there any graduate students here? I don't see any graduate students. Then I won't tell my story. But anyway, I want to tell you that was kind of how it's worked that inspired some of the things that I'm going to show you. Of course, that's a picture when we're way back at Friday Harbor, and we went with Ron, took us on a marvelous cruise. But that brings back a lot of memories to many of us. But let me give you a little bit of motivation of what I'm fixing to show you, because this talk's going to be a little bit technical. Unfortunately, I don't like to do technical talks, but except to small groups of people. But in ocean optics, when we go in and make measurements in the sea, typically, you know, we're doing measurements with sunlight. They're called passive sources. And we take things into the laboratory when we do volume scattering functions and things. We use lasers, like this laser pointer right here, which is about 532 nanometers, called a WA. It's a doublet crystal right inside. Anyway, it's a pretty simple idea, but the thing is, you notice about this light, it's very coherent, as we say in physics. Now, coherence people really don't think about too much, except there's a theorem which is considered the most important theorem in all of optics, and it's called the Van Sittert-Zernike theorem. And it's a rather complex theorem, and it's written very nicely in this beautiful book by Board and Wolf, and I know Emil quite well. And I was going to tell this little story to some graduate students, but I can tell it to a general audience too. Now, Emil's quite old now, but this happened about 20 years ago, and he was pretty old then. But there was a young guy just graduated from grad school and thought it was really hot stuff. He was giving a talk on the Van Sittert-Zernike theorem, and I asked him, we're having coffee together, and I said, well, what's new? He said, well, the thing is you should, he said, you know, he said, Wolf doesn't really understand the theorem. I almost spilled the coffee out of him. I said, you got to be kidding me. He said, no. I said, he really doesn't understand. He made some fundamental errors. I said, well, let me tell you something. I said, have you discussed it with Emil, what you're fixing to show? He said, no. He's an old guy. He said, he probably wouldn't understand what I said. I said, young man, I said, I'm going to tell you something. something, I said, you're about to make a big mistake. You ever hope for? And he said, oh, no. He said, I know I'm right. Well, okay, so we're going, how are we going to miss this talk? We went to the lecture room, and certainly about where Howard was sitting in front of the podium, Emil Wolf was there. He already had a transparency ready. This young guy gets up and starts expounding on the virtues of Ulysses or something else that he didn't know anything about. And finally, when he finished, the first hand that went up was Emil's. And he got up and he said, very polite, young man, he said, I enjoyed your talk. He said, but now I'm going to show you where you're wrong. Okay? He went up and struck that transparency and he had it point by point. You know, he just kept banging until the guy just turned Snow White. He had nothing to say. I mean, totally wiped them out. And so after I said, you know what? I said, I hope you learned a lesson from that. These old guys that you think don't know what's going on, don't kid yourself. Just forgot more you'll probably ever know. You know? So anyway, it was a hard lesson, but I wanted to tell students, don't go out there and think you're the quick gun will knock down the top guy. It's not that easy. Okay? Yeah, don't think about it. Okay, well anyway, to give you a little bit about the motivation, about the business of coherence, these laser things. You know, in scattering, we always assume these things are independent scatterings of these many body systems, like we were talking about. Barney gave a very nice example of E-hubs. And the fundamental question is, under what condition do these approximations hold, and what does coherent scattering play? And I want to emphasize the forward scattering, because this is where some of the errors are going to be made. Now, in physics, we work with this thing we call the scattering amplitude matrix, which is this thing like it. But the important thing is kind of a real part, which is the modulus here, and then the phase. Well, we define the extinction efficiency Q, full power k squared g. G is the projected geometric area of the scatterer. K is the magnitude of the wave vector, as the real part of this. But you see, you can come along and just pick up another quantity called P, which is just the imaginary part of the scattering amplitude in the forward direction. Now it turns out if you plot these PQ graphs, they're very, very sensitive to comparing experimental data with theoretical calculations. And to do that, there were some things that were done back at University of Florida. Howard certainly remembers these. They were done with what were called microwave analog experiments. Because see, with microwaves, you can null out the incident field. So they could actually measure the scattering amplitude in the forward direction. And they used to make these PQ plots and used to compare theoretical calculations with them. They're very, very sensitive to any errors that you could possibly make. So it's a nice thing to have around. Well, then I got to thinking about a way to do some simple calculations on this. But I don't want to go into detail too much, but anyway, if you take the incident field and you phase lag it, let's just talk about a sphere for the moment. You see, when this light beam goes through the sphere, it has a phase lag because it's going through a region of different refractive index. So when it occurs, there's a phase lag like this, okay, compared to the incident medium. And when you subtract that from the incident field, you get this scattered field, and that's how it's defined. That's where we get this scattering amplitude at 0 degrees. And we write it as a modulus and a phase. This is real, this is the exponential part, which has both a real and imaginary part. Now in the far field region, we write it this way for the scattered field. This little minus I right here produces a pi over 2 phase shift. So we write this relative phase shift phi 0 is this way with a phi naught coming from the, we'll call it the scattering amplitude matrix, and this constant pi over 2, which is really not very relevant. Now for a sphere with radius a, Van Gogh shows that a good approximation for S of 0 is this little equation right here. Well, the only thing that's really important is look at this rho. Rho is twice the area of radius of the sphere, or the diameter, times the index of refraction minus 1. Okay? So when A is very large, this rho is very large, which will drive these terms, these oscillatory. They'll drive all this to 0. S naught goes to a real value. Okay? So this pi of 0 thing really becomes just pi over 2. So what we decided to do some simple calculations, compare them with me. I call it me, but it's really Lorentz me. Lorentz did it first, before me. But Lorentz published it in some obscure journal that nobody read. And so, as Stigler's law of eponymity has it, and for those of you who don't know what Stigler's law is, Stigler said that all great scientific discoveries are not named after the original discoverer. Okay? And that's really true to a great extent. That includes Stigler's law, by the way. In fact, he purposely did that, so he wouldn't violate the rule. Anyway, but the thing is, the simple calculation, which you can see that we did here in blue, compares with the rigorous Lorentz-Mean calculation in red in terms of this phase that we look at here. But the only thing I really want to point out here, you see, this is in units of pi, so it's pi over 2. No matter what the size of the sphere is, the bigger it gets, it just keeps converging to pi over 2. It's a constant value. And if you add some absorption, there's no absorption here, you put a little absorption, it just gets to pi over 2 even quicker, okay? Well, you say, so what? I mean, what does it all mean? Well, here's the thing I want you to think about. You got a little volume, got a bunch of little things in here scattering light in the forward direction, okay? Now the thing is, if the phase of every time that it scatters off of one of these are not jumbled in any way, or if the phases are all the same, shifted in all the same way, it means in the forward direction the waves are going to add together. The holy grail of all of Maxwell equations is called superposition. They're linear, okay? So you can add the fields. Well then think of this. If there was no phase and it didn't matter about anything, the intensities would just add, which is basically electric field squared. So if you had two particles, you'd have E squared plus E squared, which would get 2E squared, right? But if the phase is important, then when the E's add, you get E plus E, which is 2E, and when you square it, you get 4E squared. It doubled over the independent one, right? And that's the key point. The key point here is that regardless of what you look at, and this is the thing I want to show you next, we took spheroids, you said, well, you just did spheres. What if you take some oddball, like in the ocean, really not many spheres around? Well, it doesn't matter. This is a spheroid with an aspect ratio. This one was basically 2, okay? And whether you propagate along Z or along X, these are just two different curves, you can see it still converges out to the same value, pi over 2 every time. Well, what if you did cubes? Well, there's cubes. We just did a few points here. But you can see that this simple phase shift thing that I showed you earlier agrees with the exact ADDA, which means the Amsterdam discrete dipole approximation, almost dead on. So it doesn't matter what you put into the scatter, at 0 degrees, that phase shift is the same, okay? And that's a key point. So what we decided to do was the following, because that started to bother me. Well, let's take a region of space. Here we took a volume, a spherical volume that has a radius of 2 microns. This big sphere is 2 microns. And what we want to do is take this big ball, or this big sphere, and put a lot of little spheres in it. Just keep packing them in there, because you can see that if you took a big sphere and you put enough little spheres in it, pretty soon it's going to start acting like one big sphere, right? That's what you think, and that's what should happen, which is called a continuum. And that's what the whole BDA is based on. You just got a bunch of little dipoles after a while that all start talking to each other, and they build this scattering pattern for this bigger object. But then I wanted to see, well, how did it really happen? Where does it happen? How many do you have to get in there before it starts to go from one thing to the other? Well, the thing that we found was this, and I want you only to look in the forward direction at 0 degree scattering. This is the forward direction. If you just took one little sphere, that sphere has a radius of 0.166 microns, you put it in this big volume, doesn't matter. It's this red curve. This is called the Bernoulli curve. And this MSTM, I'll tell you about that. MSTM means multi-sphere T-matrix. This friend of mine, Dan Maskowski, developed this marvelous code. We did it way back for just 2 spheres, but Dan generalized it to n spheres. And what it does, it basically is the exact solution of Maxwell's equations to n spheres in any way you want to put them in, okay? It's a very exact method. Rather complicated. It's not trivial at all to do all that, and Dan did a beautiful job. But anyway, it's a code that you can get in, so we started to play with it a little bit. And much to our amazement, we found, well, this is 1 sphere. Suppose you take 2. When you take 2, it goes from here to here. But if you go from 2 to 20, which is going from here to up here, you've increased the number of little particles by a factor of 10, right? From 2 to 20. But the thing I want you to note is that this peak went from about a little over 10 to over 100. So the bottom line here is that peak is going like the number of particles squared, like we talked about earlier when the fields add, then the number of particles, which is what you get from an independent approximation. Well, if you look at the other elements of the Mueller matrix, the P12, the reduced Mueller we call it, Ken's one of the first guys to really do a great job of measuring this thing. And I guess he's become infamous almost for that set of measurements, but they're wonderful measurements. But anyway, this is what he measured, the reduced Mueller elements. This is for the single sphere, and then you can see how it metamorphoses from the 1 sphere into the many spheres. But it does change, okay, with the number of particles that you put in this big volume. And one interesting thing is this element P22. P22 sort of tells you the morphology of a particle, okay? The more irregular it gets, the more this thing deviates from 1. For the sphere, P22 is exactly 1. It goes right across there, as you can see from that red line. Or any spherical polydispersion, it's always 1. But the minute you deviate from sphericity, it starts to deviate from 1, and you can really see it in these pictures right here. But the thing I want to show you is by the time you get up to, even 530 spheres now, which is way down here, it's deviating quite a lot. And you say, wait a minute. You just told me that if I put enough spheres in there, after a while it's got to look like a big sphere. Well, a big sphere is 1, okay? Certainly not what you're looking at there. Well, so we took this calculation even further, because the more you put in, the longer it takes. So we put smaller balls, smaller little spheres, in this big sphere, and we ran it up pretty high, and sure enough, it went just like we predicted. It goes back to 1, because then the big sphere loses its graininess, and it starts to look more like a continuum. Okay, like a big solid particle. And that's what happened. So we felt good about that. All right, but the thing that I'm not feeling good about is the fact that you got this peak right here that's always staring you in the face. And you say, well, why are you worried about the peak? Well, the reason I worry about the peak is when we do measurements in the lab, the thing that we usually use is a laser. We illuminate the volume with a laser, and then we can measure. Well, you never get the real 0 degrees, but actually it's been done. I had a student do it. But you can get close, but you can see that this peak doesn't just lie here at 0, it extends out to at least 10 degrees or so. Okay? That's the key point. Now, it turns out when you plot things like the square root of the P11, you can see here for n less than equal to a couple of hundred, it's pretty linear in this region, so it's going on to square the number of particles. But as you keep getting the packing density higher and higher, it sort of plateaus out, which is what you'd expect. It's going to approach that, for a big sphere, 2-micron sphere. And the cross-section sort of goes the same way, proportional to n, though. for this less than 100 in this region. So we're seeing some rather interesting phenomena unfold here for this coherent scattering. And you say, well, but why are you interested in coherent with the lasers and all that? If I use sunlight, well, let me ask you a question. All of you have taught physics, elementary physics, and in the book we always show the young double slit experiment, right? Classic experiment, show interference. Now the thing they always tell you in a physics book is to get the coherent light, you either use a laser, fine, or you take a little screen and you put a pinhole in it, and you let the light come to a pinhole and illuminate the double slit. Well, but they never told you what the size of the pinhole was or how far away the pinhole had to be from the slits, right? No physics book I ever read ever talked about that. Well, the thing is, they never understood the Zernike theorem. Because the first question you should raise is, well, what's the coherence length of sunlight that's coming from the sun where we do all these measurements? Well, it may surprise you, it's only 60 microns. The sun is only 60 microns coherent, which is more than I can put my fingers together, of course. That's it. The temporal coherence length, which converted by multiplying by the speed of light, c delta tau, is about a micron or less. Okay? So sunlight's not coherent, as you would expect. So the thing is, if you've got a big particle, you're illuminating basically with an incoherent source, which means if you do mean theory and all that, which is always plane waves, which are infinitely coherent, right? It's not going to work. And most people have never thought about the fact, well, never thought about that, but it's really an interesting idea. Okay? Now, the people that do remote sensing normally don't think about that sort of stuff. They're into other things, but it's the kind of thing I worry about. It's the kind of thing that Howard, of course, would worry about too. But you don't want to lose too much sleep over it. All right. So anyway, we did some more calculations. Now, we took this spherical volume and we packed it here with 50 spheres. And it was basically an optical thickness through the diameter of this thing. But the thing I want to point out is in the forward direction, you see this big green MSTM, which is an exact calculation. If you do the standard stuff, just integrating, here they're all the same size. So you don't have anything to integrate over, okay? There's one T11, and it's this red line that you get. So if you're doing a radiative transfer calculation, this red line is what you put into your code to do the calculation. But the thing I want to point out to you is if you did that calculation with a coherent source, with a laser, then what you're going to miss is all of this horrendous forward peak. But the thing is, you could get fooled, because if you look at the reduced Mueller, when you divide by this, all these other elements, you can see they're identical. Okay? They all look the same. You never know that you missed the peak unless you really measure this thing. And so we doubled it. We doubled the number of particles and put 100 in here, and you can still see this peak way up here. This would be Monte Carlo calculations. And again, even if you compare the mirrors, they're still almost identical with each other. All right. Now, we increased things even further, 200 to 400. And you can still see these peaks are always mismatched. You're always getting that phase addition in the forward direction. And you get more diffraction type phenomenon here. But in a little more deviation from the Monte Carlo calculations for all the multiple scattering that we're doing, because these are up there pretty hefty optical depth now in thickness. But you can see that the calculations would look pretty good, except, and over here, even way up to 20 degrees, they're way off, right? Way off. All right. Well, you can say, but you have all the same size spheres. They all have the same phase shift. So you expect that. But when I'm measuring in this room, they're all different sizes, right, in a unit volume. Always in our RT calculator, when we're doing aerosols, we integrate over the size distributions, all sorts of things like that. Well, it turns out it doesn't matter which you integrate over, because they're all the same. So you can see right here, we took fixed, these are the fixed spheres, this one and the solid one, and you can see that they peak again way up here, but it's lying right on top of the blue. So whether you do fixed, whether you do a Gaussian size distribution, whether you do a uniform size distribution, they just change a little bit in here. But these big phase peaks where you add the fields, they're always way up there. Okay? So it's independent of which you use and what the shape is. It doesn't matter what the shape is. You're always going to get the same result. You're always going to miss this peak. And you can see differences, of course, now in the other mural elements, depending on the morphology of the particles. Now, so we not only took the spheres, but here we took spheres, spheroids, and cubes, both in fixed orientation, random orientation. And the thing I want to point out, everything lies strictly right on the same forward peak every time. It don't matter which you run. So the bottom line is, you can't get rid of it, no matter what you try. It's always going to be there. No matter what you measure, what you do, you're going to get that big forward peak with coherent sources. Now the fortunate thing you say is, boy, I'm relieved at that because I'm doing passive work with the sun. I don't have to worry about that because it's really incoherent. Well, I'm going to show you some other things that you have to worry about when you start using passive sources, because we thought about that too. Now, the question is, how do you take a plane wave and you make it incoherent? Well, it turns out there's a whole science behind that, and I don't want to go through all these equations, they're complicated, but anyway, you can do it. It's what's called mutual coherence function, and this was done in a very nice paper called the Gaussian shell model, which takes an incident wave with coherence length. Now we can actually introduce a length of coherence, like the sun, for example, and it gets rather complicated. We go through what's called a correlated matrix and random fields, but it's kind of a Gaussian-like thing with this sigma mu, which is the measure of the degree of coherence of the light. And you can relate it to the scattering Mueller matrix by some rather complicated mathematics, which is not really that important. So what I want to show you is the results of that. So if we take the old single sphere plane wave guy, we get this black curve right here. That's the old recalculation. But what I want to show you is, suppose you scramble the coherence to make it only coherent over the wavelength of the light, which is this red curve. And you can see now in this region, you get quite a deviation in here from the recalculation. So if you even just took a single sphere and you put a source on it that was only coherent over the wavelength of the light, it's still bigger than the particle. Because this particle is only 0.32 roughly in diameter. Okay? You're going to have a problem. So we dropped it down. We'll look right here at the blue where it's the radius of the particle. Coherent length is exactly the radius of the little sphere. And now you can see you get enormous deviation. So when the light is coherent, just over the same diameter as the particle, you're already going to get bad results. That's the thing that I want you folks to start thinking about, particularly in the remote sensing area. Even though you're using passive sources, when you're illuminating things bigger than 60 microns, you're basically illuminating with an incoherent source. So when you try to compare things with B theory or whatever, MSTM, FDTD, PSTD, ABB, I don't care what it is, you're going to have a problem, and a big problem. All right. Well, this is just some more of the same, showing you these big deviations that you get. And so, again, you can increase the volume size. And when you start to increase the volume size, you can see that now you can start to get deviations even in the other elements of the mural. So now you not only start to affect, even though we can bring, whoops, we go back to that one more time. Even though we can bring this peak down, you see, by shifting to this incoherent source to get rid of that peak. When you get rid of this peak, you introduce other problems in other places. So it's like trading a headache for dyspepsia. Okay? You think you're better off, I got rid of it, oops, it got me over here. Right? That's not a good thing. So you got other things now to worry about. Now I want to point out to you, this is just fresh off the calculation. I hadn't polished this up or anything. I mean, we're still doing this and still finding interesting things to look at. So these are basically our conclusions of that. The forward direction is always coherent regardless of the shapes and sizes. And it's almost independent of orientation and the shape of the scatters. And with decreasing coherent lengths of the instant wave, the phase function forward peak decreases, but you get problems other places there. Okay. Now I want to switch over briefly to another subject. And this was inspired by Howard's work on E-Hux. And so I got to thinking, well, gee, you know, my colleague Twardowski was out there measuring these diatom chains. All of you have seen, I'll show you some of these things. They're long chain, but this is kind of motivation. It's not. But here they are. Now the thing he was worried about is the fact that you see how when these are currents going by, these chains actually align themselves in the stream. That's a hydrodynamically favorable orientation to align with the current, right? Well, the thing is, when you scatter off a unit volume, we always assume things are randomly oriented, right? And you do with the average and all that. Well, these things aren't randomly oriented. You can see they're very well aligned. So the question is, does that produce any noticeable signal that can be measured? And the answer is, yes, it does. Well, but the thing is, these are big guys. Okay, that's 1 millimeter right there. These are real big guys. And here you see the chain, that's 100 microns, and they're chained together. And I've always been amazed at how these things link up like this, and what's so interesting about why they do it that way. Now, there's got to be a reason. I mean, nature has had 100 million years, hundreds of millions of years to play with these designs, but somehow that's a good design, and it's thrived this long, and it'll probably be here when we're gone. So it's cool, whatever it's doing there. And I'm not going to go out and start to hypothesize a bunch of crazy ideas on it. But anyway, this is what a single cell looks like in that chain. That chain up like this. All right. Well, the thing is, to model this is not easy if you want to try to do it right. What we wanted to do is see if there was an easy way to do it, okay? Because I know, given an infinite amount of machine time and infinite capacity computers, we could do it, okay, no matter what, if you live long enough. That's another key. All right, so what we're actually able to do is take this guy and model him pretty well. We can give him his outer shell refractive index. We can give the cytoplasm inside a refractive index. There's a little core right here. We can give it its own refractive index. So it's a rather complicated system which is based on a prism. It's a triangular prism, okay, a coat around it, and some junk inside. And it's got a couple of little spines sticking out here on either end. That's not simple to model. It's rather complicated to model. And you say, well, yeah, but we can do the ADDA and all kind of good stuff. Yeah, but the thing is, you got to remember how big these chains get. They're enormous, okay? You can only handle size parameter of about 100 with ADDA, and then you just run out of everything. So we're looking at another method to see if we can handle this. So we came up with this thing, and we gave it this acronym, MBIT. And MBIT stands for Many Body Iterative T-Matrix Method. It's really a mouthful. But it's a very complicated scheme. I don't want to even get into the mathematics of it. But basically what it says is you can take these guys and you can do a T-matrix on these, and then you can couple these identical entities together to build bigger things. That's why we call it many body, because you can hook many of these little bodies together to make a big many body system, which is what we have. And so we can handle these smaller sizes up to a size parameter of at least 90, all right? But then we can chain as many of these guys as we want together. And that's why we developed the method. Now, to test it, we had to verify it, so we had to compare real matrix. We tested the T matrix against the ADD for this basic triangular prism that you see right here. And these are the results for P11, the phase function. And these are the reduced Mueller elements. You can see they're disgustingly close. Okay? So the agreement is beautiful for this rather complex system. And we're hitting it in an arbitrary angle of 40 degrees along here and a different azimuthal angle. But that method still takes a lot of time, very time consuming. So we decided to try a new method. We call it RBR, ray by ray. Okay? It's kind of an offshoot. My colleague, Ben Yang and Blake B, had this method called Physical Geometric Hybrid Optics, PGOH method. Okay? And this is kind of an offshoot of that, but it's got a little more stuff added into it in terms of far field, anomalous diffraction, all kind of neat stuff, and edge effects. But anyway, it's doable. And we can do an accurate far field mapping in terms of volume interval equation. The nice thing is we can handle these faceted particles, and you can obtain analytic results. And that was done with this hybrid method that we talked about here. So we want to compare the PGOH with our RBR, the new method. And this is a typical example. You can see everywhere it's dead on. Okay? So this new method, the RBR, works again disgustingly well for very complicated particle shapes. Now, when we put the multiple cells together, okay, this is one cell, this is two, we split two, and this is three, the curve right here. The thing that you notice, though, in terms of the extinction efficiency, there's really not that much difference in those when you stick them together. When they're in random orientations, and n is the number of diatom cells. Here we did some Euromatrix comparisons, okay, between these. And again, you can see that the agreement is very, very good. And well, this is showing we had phase differences, all sorts of things that have been built into this new method. It's not trivial. It's not a trivial method, but it works extremely well for these soft particles. Now, please remember, I'm talking about soft particles. These are particles with not high refractive indices relative to water. And most of the things in the ocean are soft, okay? You just don't go see a big piece of diamond floating around in the ocean, right? With an index of 2.5 or something. Doesn't happen. Okay. Well, this is just more of a comparison to show you that everything does agree nicely, whether you're doing single cells or multiple cells. And so we have this new method we call it, this is when we put the invariant embedding T matrix compared to RBR when we start putting multiples together. And again, we're getting very nice agreement between the two. Scattering efficiencies, and look, you don't even have to go to large sizes. You see, you're only up here about 7 or 8, 6 or 7 right in here, and the agreement is quite good, which you wouldn't even expect geometric optics to even come close to holding. But it does. When you put in all the bells and whistles, you can force it into being a good approximation. So the conclusion is that MBIT can be employed to get the scattering properties of the mini-body problem for arbitrary shapes in the unit cell. The size parameter, the largest suit cell can be around 90. The RBR can be employed to get the scattering properties of salt particle and intermediate larger size regimes. The scattering of diatom chains can be obtained in terms of embed and ion methods for any sizes. And when the interactions among different cells are negligible, the scattering properties of multiple cells can be obtained in terms of those of a single cell, and the effect of phase difference caused by translation of the centers. And this is the key point right here. It turns out that these diatom chains, if you just put the phase lag in the right way, you can do it very simply, just using these methods that we talked about. You can neglect all the interactions between them, just account for the phases the way it goes through. You don't have to go through these bone-crushing calculations, which is nice. In other words, they're separated just the right length to keep all the multiple stuff down, and you can do it simply. Well, not that simple, but you can do it. It's all doable now. Right? So now we can handle, not only are we doing linear diatom chain, but some of these things go in little circles, little semicircles, odd-looking things that my colleague Malik Shami sent me some pictures that he did of these little semicircular chains that were big. We can do those, showing big backward peaks. And the backward peaks, by the way, in my opinion, can only be explained one way. They have to come from faceted particles. They cannot come just from anything, all right? They have to be faceted. Either the facets produce big reflections, just like a mirror sitting down there, or the sphere, which has that unusual property at 180, okay, the globe. But that's rare, right? So that's the way it is. And that's it. Okay, I can conclude, and I thank very much for your attention.
One quick question, maybe, before we get to...
Well, you've given us a lot to think about. You know, people wonder what causes the backscattering in the ocean. Backscattering in the back. And I guess my question for you is it because we've been using lasers to measure the backscattering as opposed to using nuclear light?
I don't think it's, well, let me just say this, Howard. You know, there's a weak peak at 180 degrees. It's called Anderson-Onkelzevich. You don't know about that. But it's not, it's a tiny little peak. It's not, and it's very close to 180. It's only milliradians away. So it's not this big, no, this stuff that Chami sent goes from like 140 maybe to 180. It's a big peak back there. And I don't care what kind of particle you use, what technique, it doesn't matter. Any particle that's irregular, but if it doesn't have a lot of these plates that can reflect light, is never going to give you back. You know that. You run thousands of particles. They all look pretty much the same, and you absorb them. You just kind of go up and plateau out. You put the spheres, you get the little glory at the end.
But when you did the Gaussian Shetland, your phase function from about 20 degrees to 180 changed significantly.
Absolutely.
That's the light change.
Yes. So your question is, could that be due? Well, I don't know. What, are you talking about the satellites?
If you use meter, okay, meter assumes it's coherent.
Yes.
So you use meter, and you get a phase function, and it doesn't agree with your measurements, which maybe is bright speeds, which run what it's called bright swing. Okay, you don't get the right backscatter. You can't make the backscatter agree. Is it negative because the theory assumes the light is coherent, but the measurement with the bright swing is without coherent?
Could be, absolutely. Yeah. And that's something you really got to look at carefully. And that's why we just started looking into this, because I wondered why, you know, you see, the thing that's bothering me is, like Twardowski and those guys, they do the measurements with a laser. So he's measuring close to zero with the laser, but then we're going to take that result and we're going to apply it you know, to do radiative transfer where we look at the particles and do an average and all. But the thing is, they're not going to agree. It's a horrendous difference. You know, if you make the measurement with an incoherent source, and it's kind of easy to do. I think, Ken, you could probably put a wedge in there to destroy the coherent field across the laser, and probably you can kill that peak, and you'll get the right result. You know, if you do it from using sunlight, where you're doing all the measurements, right? We don't put
But I mean, it's the appearance of the effects of mostly the forward directions. The back.
Yeah, no, but what Howard was saying, when we went and saw the big difference, when we start cutting the peak down, if you get it small enough, you can affect it all. You cut the forward peak down, but you screw up the backward side. Yeah. Yep.